So this video is going to include me solving two problems from section 4.5. So I'm going to graph two functions from section 4.5. So I'm just going to pick two arbitrary problems. Now I'm not going to pick problems from the homework. I'm going to pick other problems to give you more examples to look at. So I'm going to begin with problem number, I'll start with problem 12. All right, there's nothing special about any of these problems. So I'll start with problem number 12. Now, problem number 12 is y equals x divided by x squared minus 9. All right. Now, before we can graph, before we can do any of the work, we need the derivative and we need the second derivative. So the very first thing we have to do is find the derivative. Right? Now, all of us know that's a product rule and we know all know how to find the derivative. So I'm going to cheat and I'm going to find the derivative on the calculator so we can have the derivative quickly and that way we can move forward. So give me a second here. So I've got x divided by the quantity x squared minus 9 comma x. So my derivative turns out to be, y prime turns out to be minus x squared plus 9 divided by x squared minus 9 squared. Okay, that's what we get for our derivative if we take the derivative of x divided by x squared minus 9. And then our second derivative, which we're also going to need, right? So I'm going to ask the calculator to do that for me. The second derivative, comma 2, turns out to be 2x times x squared plus 27 divided by x squared minus 9 cubed. All right. So we would have to find those by hand, but to speed things up, I just found them on a calculator. So how do we begin? We begin with the domain. All right. So the domain, and I'm going to do this kind of quickly because I'm assuming you can stop and start the video. The domain here, x squared minus 9 cannot equal 0, which means x cannot equal plus or minus 3. Okay, so x cannot be plus or minus 3. And I'm not going to write every single step out and write out all the detail that I would expect from you on the test either. I've showed you that in detail in class. B, we're going to find intercepts. So if we look for the intercepts, we know that the x-intercept is found by setting y equal to 0. This is a fraction. Fractions equal 0 only when the numerator equals 0. So the numerator is x. I set that equal to 0. I get x equals 0. That's now the y-intercept as well, but we'll go ahead and write the step over here. If we were going to find the y-intercept, we would want to set x equal to 0. That would give me y equals 0 divided by 0 minus 9, or 0. Now, I, again, have mentioned this already. I like to draw the graph as I go, right? So I'm going to come over here to this part of the whiteboard, and I'm going to start graphing my function. Right now, I have an intercept right there. That's all I know. Now, from here, part C, right? Part C was symmetry. And we begin with even. We say a function is even if f of x equals f of minus x. F of minus x turns out to be, I'm going to put a minus x in there. That's minus x. Down here, I get minus x squared minus 9. That gives me minus x over x squared minus 9. That is not f of x. So f is not even. But now I have to check odd. To check odd, we get f of x equals minus f of minus x. Minus f of minus x. That's what I just found multiplied by -1. So if I multiply this by -1, it gives me negative times negative, I get x. On the bottom, I get x squared minus 9. That is f of x. So f is odd. Now that means origin symmetry. So we have origin symmetry for our graph. Our graph will have symmetry with respect to the origin. Now part D is asymptotes. We'll start with the vertical asymptotes. Now to find vertical asymptotes, we look at our function. We use the simplified version. That's what we were taught in pre-calc. This is already simplified. So we set our denominator equal to 0. That gives us x. That's a difference of 2 squares. So I have 2 vertical asymptotes. I have a vertical asymptote at 3. So I'm going to come over here at 3. And over here at -3. And I'm going to put in my vertical asymptotes. Now we check horizontal asymptotes. Now typically here we would take the limit as x approaches infinity of f of x. So for us, that would be the limit as x approaches infinity, and we have x divided by x squared minus 9. So our rule says you take the highest power of x and you divide everybody by that. So that's the limit as x approaches infinity. This is x over x squared divided by x squared over x squared minus 9 over x squared. And I misspoke. It's not the highest power of x. It's the highest power of x in the denominator. All right. So this simplifies to the limit as x approaches 0. X divided by x squared is 1 over x. This simplifies to 1, and that's 9 over x squared. Well, as x goes to infinity, this is going to be 1 over infinity. That's going to be 0. That's 1. That's 9 over infinity, and we get 0. So we have a horizontal asymptote at 0. As we move to positive infinity, we now need to check the limit as x approaches negative infinity of f of x to see what happens on the other side. But we know we have origin symmetry at the same time. So do we really have to check this? Because we know if we have a horizontal asymptote over here at 0, because we have origin symmetry, we're going to have a horizontal asymptote over here at 0. In addition, we could use pre-calc to find that, right? The degree of the numerator is 1. The degree of the denominator is 2. We said in pre-calc, if the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. That's what we said in pre-calc. So there's a multitude of ways we could have found the horizontal asymptote. Now, where do we go from here? Well, we go to E, right? E, do it up here, is increasing versus decreasing. So we take the derivative and we set it equal to 0. Now we found the derivative right there, right? Now we know that derivative is going to equal 0 when the numerator is equal to 0. So we take the numerator now that has no solutions. You can't square a number because that's going to be positive, add 9 and still get 0. Then we ask ourselves, when does the derivative fail to exist? Well, that's going to be when the denominator equals 0. And we already know when that equals 0. We solved that over here. Somewhere. Where did we solve it? Right here. That gets us x squared minus 9 equals 0. And that gets us x equals 3 or x equals negative 3. Now, those are not going to be critical numbers. It's important for us to realize that. Those are not going to be critical numbers. Why? They're not in the domain. To be a critical number, you have to be in the domain. Now, when I do the sign test, I'm going to write down my factors, minus x squared plus 9, x squared minus 9 squared, right? Those are my two factors. And I'm going to write down all of my, I have no solutions here. I have negative 3 here, and I have 3. I'm still going to put them down for the sign test, but they're not going to be local mins and local maxes. The function is not defined there. They can't be mins or maxes. Now, let's take a look at what we have here. Let's look closely at what we have. This bottom term is squared. When we square something, it always turns out to be positive. Okay, it always turns out to be positive. The top term, x squared plus 9 is always positive. Multiply that by negative, this turns out to be minus, minus, minus. So we have a negative here, a negative here, and a negative here. So f is decreasing. Now we have to be careful how we write this. On negative infinity to negative 3, right? Union negative 3 to 3, union 3 to infinity. We can't say it's decreasing everywhere. It's not decreasing at these asymptotes. Right? It's not decreasing here. It's not defined there. So we have to be careful how we write that. And we got to justify why. Because f prime of x is less than 0 there. Now, we don't have any more increasing and decreasing because this function's decreasing in all of our intervals. We don't have to write anything about increasing. Now, I'm going to clean off the whiteboard over here. Now, remember, I like to write things down on my graph as I go. So I'm going to come over here to my graph, and I'm going to make a line underneath my graph. It's just a line. It's a reference line for me. And I'm going to put this information on that line. Here's negative 3 right here. Over here, I'm going to write decreasing because my function is going down. In here, from negative 3 to 3, I'm going to write decreasing because my function is going down. Over here, from 3 to infinity, I'm going to write decreasing. This is here to help me draw the graph. That's why it's here. Now, our next step, right? Our next step after this, after step E, step F is local mins and local maxes. We don't have any local mins and maxes. Decreasing, decreasing. That's not a first derivative test says that doesn't change signs. That's not a min or a max. Decreasing, decreasing. First derivative test says if it doesn't change signs, it's not a min or a max. So we have no local mins and no local maxes. Our next step, right? Our next step from here, our next step is to do concavity. Now to do concavity, we take the second derivative, right? And we set it equal to 0. Now that's going to equal 0 when the numerator is equal to 0, right? When the numerator is equal to 0. So we have 2x times x squared plus 27 equals 0. That gives us 2x equals 0, or x squared plus 27 equals 0. That one says x equals 0. This has no solutions. X squared plus 27 can't be 0. Those are both positive numbers. And then we ask ourselves, when does our second derivative fail to exist? Well, our denominator is x squared minus 9 cubed. That clearly equals 0 at x equals plus or minus 3. We've solved that twice already. Now we do our sign test. Now, what do we have? We have 2x, right? We have x squared plus 27. We have x squared minus 9 cubed. And our points are -3, 0, 3. Okay. I need a number smaller than -3. So I'll take -4. -4 times 2 is negative. I need a test point in here. I'm going to choose -1. -1 times 2, negative. In here, I'm going to choose 1. 1 times 2, positive. In here, I'm going to pick a number bigger than 3. 4. 4 times 2, positive. Now, what about x squared plus 27? Well, that's positive everywhere. When I square my x, I get a positive. When I add 27, positive. What about x squared minus 9? Well, I put a negative in here, right? A negative, like -4. -4 squared is 16. 16 minus 9 is positive. Positive cubed, positive. Put in -1. -1 squared is 1. 1 minus 9, -8. Cube -8, you get a negative. Put in a 1. 1 minus 9, -8. Cube it, you get a negative. Put in something bigger than 3, like 4. 4 squared, 16. Take away 9, positive. Cube it, positive. So we get negative here. We get positive here. We get negative here. And we get positive here. So F is concave down on -infinity to -3 union 0 to 3. F is concave up on -3 to 0 union 3 to infinity. Now, what about inflection points, right? What about inflection points? Well, we said inflection points is where concavity changes. Now, be careful. Concavity changes right here, but -3 is not in the domain. Concavity changes here. So x equals 0 is an inflection point. Three is not an inflection point. Concavity changes, but 3 is not in the domain. So this is my only inflection point right here. And I don't even have to find it on the graph. It's already labeled for me. Now, again, I like to do the graph by putting a number line down here. And I'm going to put my concavity down here to use as a guide when I draw the graph. From infinity to -3, I'm concave down. Concave down. From -3 to 0, right here, I'm concave up. From 0 to -3, sorry, 0 to +3, I'm concave down. From 3 to infinity, I'm concave up. Now I'm going to draw my graph. All right? Now I follow this to draw my graph. So over here, I have to be decreasing and concave down. Now I have a horizontal asymptote, and so I either have to go like this or I have to go like this. It's one of the two. Well, that's concave up and increasing. So it can't be that. It has to be this. What's going on in here? Well, I'm decreasing and I'm concave up. So I'm decreasing and I'm concave up. But that's an inflection point. And now I'm concave down and still decreasing. Concave down, decreasing. Now I'm decreasing, but I'm concave up. Well, if I was going like this, first of all, I'd be increasing and I'd be concave down. So that's not my graph. My graph goes like this. And if we look at our graph, it has origin symmetry, just like we said it would back in the beginning. Step C said origin symmetry. So that's number 12. Start to finish, that's number 12. Okay. Now I'm going to do one more. I told you I'd do 2 of these. So let me clean off the whiteboard. Wrong book. So I'll do number 25. Sure, that one looks fun, right? So we'll do 25. So 25 is y equals the square root of 1 minus x squared, all divided by x. Now again, we're going to need the derivative of this, and I'm going to find it on the calculator. So I have a numerator of the square root of 1 minus x squared divided by, and my denominator is x, then I put in comma x, and I get this. I get minus the square root of 1 minus x squared, all divided by x squared, minus 1 divided by the square root of 1 minus x squared. Now that's what the TI-89 told me. Now I'm going to have to tell it I want a common denominator. So I'm going to have to F3 and ask it to get a common denominator of this right here. And when I hit enter, oops, I've got a parentheses. I get minus 1 divided by x squared times the square root of 1 minus x squared. Okay, so that's what we get if we get a common denominator. Now we need the second derivative, right? We need the second derivative. So we'll ask the calculator for the second derivative. So I'll say F3 differentiate, and I'll ask it to find the derivative of the expression with the common denominator, comma x. And once again, I get something without a common denominator, so I'm going to have to do the common denominator trick again on the calculator. And it gives me minus 2, strike that, it gives me 2 minus 3 x squared divided by x cubed times 1 minus x squared to the 3 halves. Okay, so that's what I get for my derivatives. So now we start the problem. We start where we always start. We start with domain. Now here, the domain is going to be a little more involved. First of all, x can't be 0. Right? X can't be 0 because right here, we can't have a 0 in the denominator. But 1 minus x squared has to be greater than 0. That's got to be greater than or equal to 0. That means 1 minus x, that's the difference of 2 squares, 1 plus x has to be greater than or equal to 0. So I'm going to have to do a sign test when I find my domain. So what do we have? We have 1 minus x, 1 plus x. This is 0 at 1. This is 0 at negative 1. So we're going to have to do a sign test. Plug a negative in here, like negative 2, we're going to get a positive. Plug 0 in here, we're going to get a positive. Plug 2 in here, we're going to get a negative. Plug negative 2 in here, we're going to get a negative. Plug 0 in here, we're going to get a positive. And plug 2 in here, we're going to get a positive. So we get minus, plus, minus. Well, the only thing we can have is greater than or equal to 0. So from here, x has to be an element of negative 1 is okay. That's okay. We're not allowed 0, right? We're not allowed 0. Union 0 to 1. That's our whole domain. That's it. That's all we have. That's our entire domain. So when we draw this graph, if we find any critical values or any numbers that don't fit within that interval, then we can't, right? We can't use those. Okay. So after domain, we have to do intercepts, right? And what do? We do x-intercepts. We set y equal to 0. And we get 0 equals, and 0 is going to equal the square root of 1 minus x squared, right? That's the numerator, and that's when fractions equal 0. So this fraction equals 0 when the numerator is 0, and that equals 0 at x equals plus or minus 1. So here we go. We're going to start drawing our graph. Here's 1. Here's negative 1. Now, everything over here, I'm going to shade this in green because I want to remind myself I'm not allowed to go over here, right? This isn't in the domain. Everything over here is not in the domain. This is not in the domain. So where do we go? Well, we have an x-intercept of 1, right? So I'm going to go ahead and draw that on my graph. And an x-intercept of 1. I have a y-intercept of negative 1. Right? That's my intercepts. Now so I have an x-intercept of negative 1 and an x-intercept of 1. Now I need to look for my y-intercept. How do you find your y-intercept? You set x equal to 0. But x cannot equal 0. 0 is not in the domain. So we have no y-intercept. So there we go. There's our intercepts. C, we do symmetry. Even f of x equals f of minus x. F of minus x equals the square root of 1 minus x squared over minus x. Well, minus x squared is just x squared. That's not f of x. So now we do I. F of x equals minus f of minus x. So we take what we just found, we multiply by -1. They cancel. That is f of x. F is odd. So we have origin symmetry, right? Origin symmetry. That's what that means. Now D, we look for asymptotes. Well, we have a vertical asymptote because this is already simplified. X equals 0 is a vertical asymptote. So we should draw that in our graph. We don't have a horizontal asymptote because if we try to find one, right, we know how to do this. We take the limit as x approaches infinity. Look at your picture. X can't approach infinity. X can't go past 1. So you don't have a horizontal asymptote because x can't approach infinity. So out on those. A, B, C, D, E, right? E is increasing and decreasing. So what do? We take the derivative. We set it equal to 0. Well, looking at our derivative, that means we have the square root of 1 minus x squared equals 0. That gives us x equals plus or minus 1. Then we ask ourselves, when does our derivative fail to exist? We look at our derivative, we have x squared on the bottom, x squared equals 0, x equals 0. So we do our sign test. We have 0, we have 1, and we have -1. We have minus a square root, and we have x squared. Well, x squared is always positive. Did you notice what I did wrong with the sign test? We don't have any points on that side of -1. We don't have any points on this side of +1. That's all we got to worry about. Now, square roots are always positive. If you multiply by a negative number, you get a negative and a negative. This is negative and this is negative. So f is always decreasing. That's what that means. And just like on the last problem I did on this video, we have to make sure we write it down very, very carefully. All right, we got to make sure we write it down correctly. We have to say f is decreasing on, well, let's go back to it. -1 to 0, union 0 to 1, right? That's where we're decreasing. Because f prime is less than 0 there. Now, f is never increasing, right? It's never increasing, there's no plus. So we don't have any local mins or local maxes. That's 2 problems in a row with no local min nor a local max, right? The last problem I gave you didn't have one, but both examples I did in class had them. Just happened these 2 examples don't. Why aren't there? Well, because we don't change signs. The first derivative test says you have to change signs. We don't. Now we do concavity. So we take our second derivative, we set it equal to 0. Our second derivative is this, right? So when is that going to be 0? When the numerator is 0. We bring the 2 over, get rid of the negatives. X squared equals 2/3. X equals plus or minus root 2/3. That's actually inside of our domain, right? That's inside. When does the second derivative fail to exist? When x cubed, right? The denominator could be 0. That's 1. That gets me x equals 0. Or when 1 minus x squared to the 3/2 equals 0, right? That's when it's going to fail to exist. This is going to get me x equals plus or minus 1. So now we run our sign test. We have 1. Well, of course we have 1. That's where we start, right? That's where our world starts. Our world ends at 1 and -1 because that's our whole domain. We have 0. There it is. We have minus root 2/3. And we have plus root 2/3. Now, I get it. You don't know what number that is. I'm with you on that. You don't know. Okay, don't panic. What do we have? We have 2 minus 3x squared, right? That's our first factor. We have x cubed. That's our next factor. And we have 1 minus x squared to the 3/2. Okay, now we got to pick test points. Now, you need a number that's in here, but you don't know what this number is. Okay, I agree. So pick negative 0.9999999. Pick this number right there. That way, you know you're not going to miss the interval. Pick negative 0.9999999. Okay, negative 0.9999999. And now do the math. Negative 0.99999 squared is positive 0.9999999 times 3. That's really, really close to 3. But it's negative. So that's negative 3 plus 2. That's going to be negative. What about in here? Well, pick a number really close to 0. 0.0000000000001. A number really close to 0. It's negative, but when I square it, who cares? Now I have negative 3 times 0.00000. Pick this number right here. When you multiply that by negative 3, you get this. Now, add 2. That's going to be positive. If you pick that number, take away the negative, square it, it's still going to be positive. Multiply by negative 3. Now it's going to be negative again. You're going to get a positive there. And you're going to get a negative here by picking 0.9999999. That's what you do when you don't know one of the numbers and you don't have a calculator. You just pick a number really close to the end point, and that way you know you've got it correct. Now, that's cubed, right? Cubed. This is negative. When you cube a negative, you're going to get a negative. This is negative. So when you cube a negative, you're going to get a negative. In here, I get a positive. When I cube a positive, I get a positive. In here, I get a positive. When I cube a positive, I get a positive. What about here? You're going to pick 0.999999999. Okay. When you put that here and square it, you get a positive number that's smaller than 1. 1 minus that's going to be positive. You take the square root, positive. You cube it, positive. What about over here? We're going to pick 0.0000. You're going to put that there. You're going to square it. You're going to get more zeros. 1 minus that's going to be positive. Cube it, positive, square root, positive. Here you're going to pick in and you're going to get plus, and here you're going to get plus. So what do we get? We get negative, negative, positive, so we get plus there. Negative, positive, we get negative there. Positive, 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 we get positive there. And here we get negative, positive, positive, we get negative here. So I'm gonna, oh, I forgot to put my line over here, didn't I? I apologize. Let's get my ruler out. Let's get my line over here. I forgot to do my line for increasing and decreasing. Luckily, I didn't erase that. So here, between -1 and 0, we're decreasing. Between 0 and 1, we're decreasing. Now we have to do our concavity, right? But we have it right here. So we'll draw our line over here. Right? We'll draw our line. Now from -1 to whatever that number is, we'll just put it right there. From -1 to that number, we're concave up. Then from this number to 0, we're concave down. Now from 0 to this number, we'll put it right here. We're concave up. And from that number to 1, we're concave down. So this is an inflection point right here. It's in the domain, so it's an inflection point. This is an inflection point. It's in the domain. This is not an inflection point. It's not in the domain. Now we can draw our graph. Now we have to put this, right? We've got to put this number. We need the y value for this. We don't know where the y value is right here. So we're supposed to stick that number in there. Now we all took algebra 2. We can do that, right? We can do that. So we're going to go 1 minus the square root of 2/3, right? That's my x. I'm going to do the positive one. It's going to give me the same value as the negative one. We have origin symmetry, so whatever they're going to be, one's going to be plus, the other one's going to be minus, so we can just use our origin symmetry. So I might as well put the positive one in. It's going to be easier. So I'm going to take that. That's there. Now I have to square it, right? Because that's squared. Then I got to take the square root, and then I got to put it down here. Okay. Now we all took algebra 2. We can do this. When I square the square root of 2/3, I get 2/3. 1 minus 2/3 is 1/3. Don't forget the square root. So I got the square root of 1/3. Down here, I have the square root of 2/3. Well, we all took algebra 2. That's the square root of 1/3 divided by 2/3. 3 cancels 3. That's the square root of 1/2. So when I plug this in, here it is. I'll just put a dot there, right? I'm just going to put a dot. That's an inflection point. And my coordinates, I'm going to write them down, right? My coordinates are root 2/3, comma, root 1/2. Now I have origin symmetry. So this one, right? This one's going to be right here. It's going to be an inflection point, so I'll put an IP on it, and it's going to be minus root 2/3 minus root 1/2, because origin symmetry means I have to be symmetric with respect to the origin. It's odd. Now I can draw the graph. So I start. I have that dot. That's where my graph begins. I'm decreasing. I'm concave up. So I'm decreasing and I'm concave up. But then I'm decreasing and I'm concave down. Don't forget your asymptote. Decreasing, concave down. There we go. On this side, I'm decreasing, I'm concave up. Here's my asymptote. Now I'm decreasing and I'm concave down. Don't forget, we stopped right there. There you go. Origin symmetry. All right, so there's 2 more examples for you from section 4.5. I did problem 12 and I did problem 25.